Hello and welcome to the surface shading lecture within the course of computer graphics at KAUST. Today we will be recapitulating and bringing under some different light the knowledge which we already obtained from the lectures on ray tracing and from the lecture on graphics pipeline. So we will be talking about various illumination models, and we will again review the diffuse shading, also called the Lambertian illumination or the Lambertian reflector. In this illumination model, we define that the shading, the level of how much illuminated a particular surface point is proportional to its to the direction of its normal and to the light vector. We can assume one way to assume could be that the light vector is constant for the entire scene, meaning that the light source is very far away and therefore the changes in the light direction are not very prominent between the different elements within the scene. This is one way, and we can call such a light source a directional light source, and this will simulate somehow the light source of the sun. But we can have also point light sources, which will be light sources which are more closer or part of the scene, where at each point there will be a different, at each point on the surface, there will be a different light vector. It doesn't change anything, however, on how the shading will be computed. So the angle between the light vector and the normal vector are giving us the amount, the proportion of the illumination of that light source on that surface point. Now, this can be expressed through cosine term, because the cosine is having the strongest value or the highest value when these two vectors are, when the dot product between these two vectors is 1, meaning they are aligned with each other. And then the cosine term will be 1. And when they will be perpendicular, the cosine term will be 0. So the more spot on the light source is with respect to the surface point, the more illuminated this surface point will be. And we know that already from the previous lecture. But now we will bring some other elements to this characterization, namely the diffuse reflectance, CR here, which we can also call as the material color of that object. But bear in mind that this is only the term which describes which wavelengths of the light will be most reflected from the surface point or from the entire surface belonging to a particular object. This means that we can call it a color because it will be a vector in our RGB space where each color component will have a certain value. And based on how high this value is, the more that color channel will be reflected from that position. We can say that the rest of the energy which is not being reflected will be absorbed at that location. And then we have the light intensity, which can be also expressed in our RGB color scheme as a vector, RGB vector. So this is an implementation of shading which is using the RGB color space. We could have also spectral approaches where we would not just treat 3 different colors, but a more broader spectrum of wavelengths. And then we will need to deal with more dimensional vectors potentially. However, for this case, we are dealing with just three components, the R, G, and B. Also for the light source. So the light can be the same intensity in each color component, so it will be white in that case, or it could be of a different color. For example, it could be red or green or blue. And with our Lambertian shading here, we are now first evaluating the geometric characterization, and we are not taking into account the contribution from any light which is not which is outside the uh, 0, 1, 0, 90 degrees angle between normal vector and light vector. Therefore, we are having this nonlinear max term here. And then we are multiplying this term, which is a scalar value, with all the color components of the light. And we are performing here a component-wise multiplication between the light vector and the light color and the diffuse reflectance term. So this will be the way how we are performing the shading. And some of you had questions during our questions and answer sessions, how the light should be calculated. So here you have the exact formulation for that. If we are dealing with diffuse shading, it might happen that parts of our scene which are not directly facing the light will be completely dark. And this is perhaps not desired, and we know from photorealism that even under indirect illumination, objects are not entirely pitch black. They would be illuminated indirectly. This can be modeled in various ways. For example, we can have several light sources. This will lead to the fact that we will have more computation to perform. Another approach could be that we will have just one light source always attached to the camera position, and this will be very dimmed light source and will result into direct illumination from the camera point of view. So it will be view dependent light source, so to say. And the cheapest and very often used option in these illumination models which we are describing here is the simple ambient term. This means that no matter what is how illuminated the scene is, each element on the surface of our geometry will get at least some illumination from the ambient color term, here denoted as CA. So this is somehow an ambient light source, which is not weighted by the geometrical properties and the light position, because the light is coming from everywhere. But we still need to take into account the reflectance of our object, its material, so that in this way the ambient color term is component-wise multiplied with the reflectance. In order to keep the color, the light within certain bounds, we are defining that our ambient color term and our diffuse light is, or several lights, are within the range 1, 1, 1, 0, and 0, 0, 0. So you can see here that these are indeed vectors. The diffuse shading is not changing very rapidly across the geometry because it doesn't have very high frequencies, so to say. Therefore, if we have a very well tessellated scene, meaning that our objects are based or built from many small triangles, it might make sense for such a triangular scene to only illuminate or perform the illumination on the vertices and then to, to propagate this illumination across the faces of the triangles. Keep in mind that if we will be having our scene which is approximating the smooth surfaces with the triangles, as it is often the case in computer graphics, it will, and we will perform a so-called per triangle normal shading, then we will end up in very faceted illumination because we will see all these flat surfaces here, which we don't want. We want to pretend that there is some kind of a smooth sphere here, which is just approximated by these triangles. So how can we do that? Well, we can perform the illumination per each vertex and then simply perform interpolation across the triangle using barycentric interpolation so that we achieve the smooth transition between one shade, one illumination at one vertex to another vertex. And for that, we would need no longer to have the per triangle normals, as we would normally define per each plane. There would be one normal which corresponds to it, but it will be actually a per vertex normal. Per vertex normal can be calculated, for example, by averaging the per triangle normals of all triangles which are um, containing this vertex and then normalizing. This way we can calculate the per vertex normals for the entire object, and afterwards we calculate the illumination, and afterwards we smoothly propagate this illumination using barycentric coordinates so that we have a continuous transition of shading instead of this hard edges, which we would otherwise have if we would perform the illumination per one triangle and then perform the illumination for another triangle. You can see that for this triangle, at every point, otherwise, we will have exactly the same normal, which would be pointing here. So the color here will be exactly the same. And then there will be abrupt change, and here will be another, the same color. So to avoid that, we are using this per vertex diffuse shading and then using barycentric coordinates or barycentric interpolation for propagating this color smoothly through the triangle surface. But not all objects which we are dealing with are very diffuse. They would have a certain level of shininess, some some reflection, diffused reflection, however, still somehow directly from the light source, we can observe somehow not complete matte, but a little bit more objects which are going more and more towards the ideal mirror type of material. And for this, the diffuse shading is simply not sufficient illumination model. And we would need to add some more components to it so that we can model these additional highlights, which are often the case on the materials around us. How can this be achieved? This can be achieved by evaluating what is happening. How are these highlights coming in place? When we look at it, we can see if we see somewhere, if you look at our desk, for example, and we see that it is a reasonably diffuse surface, but it is also reflecting the light source from its surface. And this light source is reflected perfectly around the normal vector. So the reflection of a light source is the strongest in the so-called reflection vector. This will be the strongest reflection from this particular setting. And it can be characterized by the term angle theta or its cosine term to scale the level of highlight based on what is the position of the reflection vector and the position of the eye point, because this illumination model is dependent on the viewer's position. The more the viewer is aligned with the reflection vector, the more of the highlight he or she will observe. And the more this is misaligned, the less of the highlight the person will experience. How can we calculate the reflection vector? We already had it, but let's have a look at this very simple geometric characterization here. We have our light vector here, and when we negate that light vector, we will get to this position, minus L. So we are here. The reflection vector is minus L plus, and it says twice n dot L. So n dot L is the cosine theta. N dot L here is the cosine theta. And this cosine theta is this length. Cosine theta is this length. And it is this length as well. So twice cosine theta in the direction of the normal vector brings us to the reflection vector. Minus L plus twice cosine theta scaled the normal vector, and we have our reflection vector. Once we have our reflection vector, we can calculate our specular highlight component by having again the cosine term, which is then clamped to the 0, 1 range. And this highlight, however, is having just one frequency. It's maybe not for more glossy surfaces, it would not be a good representation. Therefore, we have this Phong exponent here, which is basically scaling this function of the dot product of the cosine term. The cosine function gets more sharp, if you like, the transition, and by that we can simulate more smaller and more intense specular highlights. So, and of course, this is dependent on the light source color. However, it is not dependent on the diffuse reflectance, because this reflection of the light source is not really sort of penetrating the surface of our material, but it's directly reflected from the surface, from the top surface of it, and therefore the color of our material is not playing any significant role, except for metals, which we will discuss. Phong illumination can be also computed in an alternative way, not only based on the viewing vector and the reflected vector, which is the reflected vector around the normal based on the light vector's position. We can compute the Phong illumination, the highlight contribution, based on the so-called halfway vector. The halfway vector will be a vector which is an average vector of the viewing vector and the light vector. So these two are already expressed. Both the viewer is expressed here and the light is expressed through the halfway vector. So we have our characterization here already of the relationship between the light position and the viewer is expressed and captured in this halfway vector. This halfway vector is normalized so that we have it of unit length. And then we are not calculating the dot product between the halfway vector and the view vector because the halfway vector is formed by the view vector, but based on the normal of our surface point. So the normal has not been expressed in the calculation of the halfway vector yet, and this the deviation of the halfway vector from the normal vector will be defining as the specularity. And the more, please notice that if the halfway vector will turn out to be exactly aligned with the normal vector, this means that the light vector and the viewing vector are perfectly aligned, and the viewing vector is in fact the reflected vector of the light vector around the normal vector. So then the contribution will be the strongest of our specular highlight. So the more the halfway vector is deviating from the normal, the bigger the omega angle is, the smaller contribution from the specular highlight at that particular position. And this can be expressed here. So we have just reformulated our highlight calculation a little bit. And here the advantage is that we no longer need to deal with the cases when the specular highlight, the dot product between the viewing vector and the reflected vector will be then smaller than 0. We do not need this max term anymore, but we still keep our Fonck exponent in order to be able to scale the transition of this specular highlight to make it sharper or less sharp. And if we put all these aspects together, the diffuse term, the specular highlight, and the ambient term as well, we will have this description of the local illumination model here. Let's have a look at it. What do we see here? So we can see here the diffuse component, where we have the dot product between the normal and the light vector, the Lambertian shading, and this is multiplying, this is scaling our light intensity vector and of each of its components. We sum this up together with the ambient light, and then this all is then reflected in a scaled way based on the color of our material. So which color component will be more suppressed and absorbed, and which will be more then emphasized. And then we have our specular term, and we said that the specular term doesn't really depend on the color of our object because it's not really, the light is not really penetrating and reflecting from there, but it's reflecting directly from its surface. And this is true for the objects like, for example, a polished wood or plastic, but it will not be the case for metals, for example. So you can see that the specular highlight calculation is here, which is scaling our light vector here and its components. And then, furthermore, we have here one more term, which is optional, where we can additionally scale the intensity of our specular highlight. this is the term CP, which can be of again various three color components, but normally this one would be of white intensity, so it will be scaling each component in the same way. Maybe I explain what is meant by this CP on this little drawing. So if we have our cosine term here, then the cosine will be scaled by our Fonck exponent here, so that we will still have start from 1 and go to 0, but we will not, our period will be different, and this transition will be different. So this is the way how our exponent is scaling the function transition. And then this CP element is scaling it here this way. So it can move it, that the whole thing will be just, the maximum will be, let's say, 0.5, and there could be different profiles of this function. So these would be the two scaling factors of our highlight. However, for the metals, the situation is different, because those are in fact taking the color of the metal in the highlight. The highlight will be containing the color of the material of the object. So you can experience it if you look at gold, for example, and you shine a white light on it, the specular highlight will be still yellow if we are dealing with yellow gold. Therefore, our CP will actually be here again CR. So for the metals, the CR will be entirely outside the equation, and will not only be the diffuse reflection, but will also serve as the scaling factor for the specular reflection. As you can see, the highlights of the specular reflection are sometimes of a higher frequency, so they are smaller, and these details with the Gouraud interpolation, where we are rasterizing for the positions in the triangle the color which is already calculated per vertex, as shown here, this would not be sufficient, because we will lose these specular highlights. We discussed this already on the previous lecture. Therefore, it would be important to perform a different type of illumination, which is called the Fonck illumination, where we are rasterizing not the colors, which are calculated per vertex. The color is calculated later per each surface point, but we are rasterizing and interpolating the normals. So with our barycentric interpolation, we are calculating from the per vertex normals the normals which are per position on the triangle, per fragment, so to say, and then we are normalizing it so that we obtain a unit length of them. And we are using then this normal vector for performing the illumination as we just described. Diffuse shading and highlights are together forming an illumination model which somehow is mimicking realistic shading or light transport. So this illumination model will somehow look like realistic scenario. It will not be very realistic. If we closely inspect the scene, we will realize that the scene is probably computer generated and not it's not a photograph, but the result will be reasonably good given its relatively low computational complexity. But the goal of these type of illuminations is to get as close as possible to the realistic scenario. But this is not the only goal. Sometimes shading models also evaluate or are trying to mimic a different type of shading or illumination, such as, for example, artistic depiction. So they are trying to simulate and how a 3D scene will be looking if it will be rendered by an artist on the canvas. And here the first aspect which we will discuss is the line drawing. So we will present a very simple model for line drawing, for drawing silhouettes as called here, but normally these lines will be called contours. So when do we draw a line if we are depicting certain objects? The line is typically when it is where the object is somehow bending away from the viewer. And this can be expressed by, if we have a triangulated scene, by the relation between the viewing direction and the orientation of the triangles. So imagine if I have here one triangle and here I have another triangle, and the corresponding normals, orientations, and I have a certain viewing direction, which is the E here, then maybe I will have different dot product cosine between the N0 and N1. However, they will be of the same sign. Depending on the orientation of E, they will be either positive or negative, but they will have both the same sign, meaning that this multiplication will be bigger than 0. And when will such an expression of the multiplication of two angles smaller than 0? Well, when one triangle will have a different orientation with respect to the viewing direction than the other triangle. So let's have a look at it, what we mean by that. If we have here one triangle, and here we have another triangle, then this would be a line which we will etch, which we will consider as being part of the contour, because here the surface is sort of bending away from us. Here is one normal direction, and here would be another normal direction for the other triangle. And you can probably agree with me that if our viewing direction here will be resulting into different into dot products with the normals, which will have different signs. So their multiplication will be smaller than 0, meaning that these two triangles are sharing an edge which is forming the contour. This can be expressed also in a different way, not multiplying creating the dot product, but between the normals and the viewing direction, but actually evaluating functional evaluation of the implicit plane, which is going through these triangles, or where the triangles lie. So this is the function of an implicit plane where we put the viewing uh, viewing vector, and as this viewing vector is not aligned with the plane, it will result in non-zero value. And the same holds for the another implicit plane, where the viewing vector will not result in the value 0, because it's not will be not generally within this plane, and their value will again, if there will be different values of these two implicit plane evaluations, then our triangles which lie within these planes and share the one edge will be forming an this edge will form a contour. Sometimes we have a situation where our where we still want to express the, or we do not have a contour or silhouette as it is called in the book, but we have maybe the triangles would be something like this, and they will still have a positive sign, both, let's say, with the dot product with the viewing vector, but they will have a very different orientations of the normals. And we would like to see here this crease, a line which will be forming sort of a crease. So we can also model this by simply, this would be a view independent approach, in fact, where we are evaluating the alignment of one normal with another one. And if this alignment is getting less and less, so these two normals are having a higher and higher angle with each other, and by that smaller and smaller dot product, then at some point they will be qualifying to form a crease. So there is a threshold value which, let's say, will be 0.1, and every edge which has two triangles which are sharing this edge have the normals, and their dot product is less than 0.1, this edge will be classified as a crease. The last artistic approach which we will discuss here is the so-called cool to warm shading. So artists are typically not only using the intensity for the shading, but also a hue. You can often see that objects which are in the shadow or are darker will be having a more of a bluish tone, and objects which are more exposed to the light source will have more of warm tones, let's say yellow or orange. And this effect used in arts is giving a very appealing representation, and is also securing that the objects are not totally in darkness or are still quite well illuminated. We can see that a standard Fonck illumination model will be represented here, where a lot of these elements, the ambient term here is so small that several objects are quite dark, or parts of the objects are quite dark. However, in the other cases, in the second case, we can see that the transition between being illuminated or not directly is changing the hue. So how can this be modeled? This can be modeled by simply having a coefficient, let's call it the warmth coefficient, which evaluates the dot product and the light vector. So it's like the Lambertian illumination here. However, it is not clamped between 0 and 1, but we are using the entire spectrum -1, 1. But with the 1 here, we are bringing it to the positive range 0, 2, and by the divider here, we are bringing it to the range 0, 1 again. So it's a different way how we are scaling the dot product. And therefore, but you can see that this is the coefficient of the warmth. So the higher this coefficient will be, the more the warm color will be expressed. And the smaller the coefficient will be, this term will be higher, and the more cool color will be expressed. We have here two different colors, the warm color, which would be something which is rather bright and has a high red component, and the cool color will be having a high blue component, as you can see here. And generally, the intensity of this color will be lower. And by this, simply by this interpolation between these two colors, we can realize the shading of this cool to warm shading, as it is called. Please note that these colors are then still multiplied with the material colors or with the diffuse reflectance, so that the colors of the actual objects are maintained, but they get a slightly different tone. While this representation looks already quite appealing, with adding the contours, as we just learned how to draw them, we can really create a more cartoon-like experience. So this will be a shading approach, which is not really aiming at photorealistic appearance, but more of an artistic appearance, and we would associate it with an appearance which looks like as it is drawn by an artist. So this was the short lecture on surface shading, and you have again recapitulated and got some more details on shading using diffuse shading and Phong illumination, which incorporates highlights. And we have been discussing also the artistic approach for depicting lines and for performing the cool to warm shading. That's all for today. See you at the next lecture.